Alright, so today we're going to get into geometric tolerancing. So this is your Unit 5. These are just your objectives. So we'll cover everything, okay, from the very beginning of your geometric controls. And then, of course, we'll hit all dimension tolerancing, your G, D, and T, okay? And T is for tolerance, and GD is for geometric, okay? Dimensions. And we go all the way down to the virtual condition, okay? We'll say one by one, don't worry about it. No need to just read it one time and that's fine. These are just your terms and definition that you need to get in touch with your ISBN 14.5N, your 1994 revision. So here from datum all the way to the dimension basic. Again, we're going to cover each one of them. And so if you read it just like one time, that's alright, yeah? And of course, you will go back to it. I'm not going to be asking you to write the definition or something like that. Okay, so let's get into material condition modifiers. So what we do in geometric dimensioning and tolerancing, we try to control the features, on your part. So for the size of your part, the function, the relationship, the location, all of them, we need to control them. Otherwise, you can't be able to manufacture them. So it's extremely important that we know each feature on the part, and also all the parts in your object needs to be dimension, needs to know the tolerance for each of the dimension. You gotta know all of it, okay? So basically, short to the point, you need to know what you're producing, and you need to know your product, and you need to know all the features in your product. And in order for us to be able to know that, we gotta do dimensioning and tolerancing. Otherwise, it's impossible for us to be able to control them. So when we do that control, we've got to understand the conditions, conditions of your part, because all the parts are made of materials. So that's where the material condition modifiers come from. So it's all about your part. Your parts are made of material. Your parts are features. Every time you have features, it comes with a dimension and tolerance, and we have to master all of that. Otherwise, it's impossible for you to draw. So if you think about a hole, then we think about a hole is a circle, so there always is a center. Since you have a center, there's an axis, So everything got to be connected to each other. Since you have a hole with an axis, then orientation and location of that is very important. When we deal with the location and orientation, here we go again, the dimension, the tolerance come with it, So you gotta understand whether the hole is at the upper part of your tolerance or lower part of your tolerance. We call that upper size limit and lower size limit. Of course, the terms can confuse you, and sometimes you don't remember the term, but at least you know that every time I have a dimension, then I've got to have a tolerance. Every time we think about the tolerance, there is a range. Every time you think about the range, there is the upper and lower limits. If you get about that much, you're okay, And all the parts are made of, again, material, So therefore, the condition comes with that material. So if you think about a hole is a circle, so therefore there is radius and there is diameter. And if you have a diameter, again, we go back to our tolerance, and you have an upper size limit and you have a lower size limit, So if the whole diameter is at its upper size limit, then there may be more tolerance for the alignment for the mating part. Meaning, like, holes are to receive another part, right? Usually fit into that hole. And we talked about that, the mating, mating. And of course, every time you have to do the process of mating between two parts, then your alignment is very important, because without the correct alignment, you can't mate them, meaning you can fit the two parts into each other, Then if the hole diameter is at or near the lower size limit, okay, of your tolerance, of course, you've got to have a greater emphasis, meaning like you have to pay attention to focus on a possible misalignment again, yeah? Hole diameter, tolerance, upper limit, lower limit. Hole function is for mating, yeah, to receive another part. Alignment, very important. Be careful with all possible misalignment, okay? Even it is an upper size limit or lower size limit. For lower size limit, you've got to be careful about the misalignment, yeah? So what you've got to do is you've got to have a access the tolerance zone specified, okay? Meaning like you got to have a specified access tolerance zone. You have to maintain that even if you've got the actual hole size, right, within that specified size limits. Meaning like we got to have a tolerance zone, yeah, for all of the alignment and misalignment, to avoid the misalignment and also to ensure the alignment, we've got to have a tolerance zone, yeah. So we break it into three parts in order for us to ensure the alignment and uh, to get rid of the possibility of misalignment between the mating parts. We come up with the maximum material condition and a least material condition. And the last one is a regardless of feature site. All right, the name of the term is going to get you. Just be, like these are the names that we use. Okay, and just don't feel bad to learn a strange and weird name like this. Okay, but you will get to it. We just call it MMC and LMC, and then RF. Okay, some people call it different way, but most commonly MMC, okay, LMC, and then your RFS, okay. Some people just write it RF. I just write like RF because I know that's regardless of feature side. But most of the text will go like RFS. You can also write in your own symbol as long as you know what you're doing, okay. All right. So maximum material condition MMC, the symbol is a little m in a circle, yeah. So this is just a condition about your material of your part and where the most material has been left in a part, okay? Meaning most material is in the part, meaning your hole is small, okay? That's what it's talking about. So a hole would be at its smaller size limit. That's the only way to leave the most material on your part, yeah? If you have like a big giant hole, of course, the material will be gone out of that part. So therefore, most material of your part with the smaller size limit, and we call that the maximum material condition. This might get you like when you read it, a shaft will be at its largest size within the limits of size. Of course, this is just basically meaning your shaft gotta get into that, all right, this size, yeah. So even and you can go as large as you can go, but only for or only within the limits of that size, yeah. And we call that the maximum material condition. You won't get it right away. It's going to take you some time, yeah, for you to actually get it. These things are something you can get by listening to lecture or reading it. You gotta get into the problem and take a look at it, with a diagram and things like that, and it come to you, yeah. Okay, right now just listen. It's just your first time listening, yeah, to what they are, and we're gonna get into the diagram and take a look at it. And as you start drawing your exercise, you will kind of get it. If you do it 2 times, 3 times, you got it, yeah. Okay, now so this is your MMC, yeah, material condition modifier, MMC, which is maximum material condition. Maximum material condition is at its smallest hole, yeah, smallest possible size. So we're looking at a circle, so therefore this hole is the smallest, yeah. So therefore leaving the most material on the part, yeah. And this of course is an internal feature, you're looking at it because hole is an internal feature in a part. So in this case, they give you some number here. So you have like a 0.434 and 0.440. This is bigger than that. It's got to be the smallest for MMC. So it's got to be this in diameter. Your symbol size is a diameter. So therefore 0.434. Yeah. And that's your MMC. So the most material is going to be in your part. Yeah. What is the value of MMC? It's right here. Choose the smallest one. Yeah. Pretty easy. Okay, after we finish the internal feature, we're going to come into an external feature. Now, so this is a little pin. Of course, you have two views that you can see. This is your hole, yeah, this is your pin, and the pin is a part that is going to go into that hole. So now we have a range right here, 0.750 to 0.756. Yeah, your MMC is going to be 0.756 because this is an external feature. Yeah, because the MMC for the external feature, not a hole but a pin, got to be at its largest possible size. Yeah, so therefore here in this case is 0.756. Why? Because for external feature, you're gonna have the most material. Yes, the most material. So therefore, the largest will maintain the most material. For internal feature like a hole, you've got to have the most material on the part. Since you are cutting through, right, that part, you don't want to take all the material. So for whole internal feature, you've got to have a smallest, yeah, possible size. So this one is your largest possible size, and that is 0.756. And this is what it's telling you. Yeah, when I say you're not gonna get it, right here, hole diameter internal. Yeah, in that hole diameter again, internal. So here we're dealing with the MMC. Yeah, with the smallest possible size. Okay, but when we come to here, we're bringing in an external feature. So at that time, you're going to have a largest possible size because the larger the external feature is, the more material your part is going to have in that feature. Yeah. So your part is a pin, yeah, which is an external feature. We're going to take the largest size for MMC. Your hole is an internal feature. Since you got to cut material out of it, we're going to take the smallest possible size because MMC means a maximum material condition where you want to leave the maximum material on your part. Okay, so pay attention to the external and internal. And then this is just reiterating, yeah, MMC. Then we'll get into LMC, little L in a circle. So that's a least material. Now you got it. You gotta leave, right? The least material. So when you cut the internal, take the bigger chunk out of it, yeah. And when you do the external one, again, it's got to be the smallest. So it's kind of like a crisscross, yeah, with the first condition, which is maximum material. This is the opposite of that. Yeah. So let's take a look at it here. Here for LMC, yes, for internal feature like a hole, since you got to leave, yeah, the least amount of material on it, we're gonna cut it through, and we're gonna take the largest possible size, yeah. So therefore 0.440 in this case. Okay, don't worry about this like color. I don't know. Yeah, this is the author doing some stuff. We have to use their slides, so it's really bad. Some of them are misleading. Anyway, so you have to choose a 0.440. Yeah. That way, you're gonna leave the least amount of material, meaning like you cut the giant through it. So that way, your part will be left with the least amount of material. External. For external is the opposite for LMC, least material condition. You are going to leave the least amount of material, so therefore we're going to choose, alright, the smaller one. Yeah. So if you choose the smaller one, then you're going to have the least amount of material on that pin. Yeah. So therefore 0.750 because it is an external feature. Yeah. It will take a little bit of time for you to get it. I'm just going because I have a lot to cover in a lecture, and I've been doing this again and again. So yes, in my head it's very automatic. All right. So now reiterating MMC, this is LMC. Then we'll get into the regardless of feature size. Yeah, this will be the next in your next handout. But for lecture, I'm just gonna go ahead and cover it all the way through. Yeah. So regardless of feature size, most of the people go RFS. You will see in some of the books they go just RF. So that means that it's just a regardless of feature. Yeah. Sometimes they ditch the size. I don't know why. You will rarely see in some of the books that don't follow the standard. I also call it regardless of feature anyway. Some people don't want to call the whole thing. So anyways, regardless of feature size, RFS in this book, just go with RFS here. Just a condition again, yeah. And your tolerance again is going to apply. And here with the name, regardless of your features, so it doesn't matter what your feature size is, okay? It's going to vary within the limits of that specified tolerance. So every time we deal with a feature size, there is dimension and there is tolerance, yeah? The tolerance is always there with the dimensions. So RFS is don't care about the feature size, okay? We're just going to go ahead and deal with the specified tolerance. Now I'll show you what they are. So the symbol again is S, and then there is a little circle in there. Yeah, so we have M in circle, L in the circle, and S in the circle. Yeah, so that's your RESME. Again, people don't use this sometimes. You're gonna see just RF or RFS in the diagram. Okay, so let's get into fundamental rules. So this is in the second handout. Alright, so fundamental rules, we'll get into it for the G, D, and T. So this is what we write: G, D, and then a little n, and then T, meaning geometry, dimensioning, and tolerancing. So basically, we're just going to go ahead and look at the design principles and also the fundamental rules, because we have to use these concepts, because it's very important in our design process, manufacturing process, inspection process. And also we have to be careful with the precision and mechanical parts, and for that we will definitely use the geometric dimensioning and tolerancing. So let's learn about this system of G, D, and T. The very first thing we're going to get into is something called the envelope rule. That's your rule 1, yeah, and it's based on a Taylor principle, yeah. So let's go into what that is. We're dealing with individual feature size. Again, don't feel bad about it. It's just a feature on a part. Your part is on the object that you're trying to manufacture, okay? Your object is your product, of course. It can be a little tiny part, or it can be the entire product. Depends on the size of your product, yeah? Mostly you will get a part of the product. And on that part, you have many different features. Sometimes just few features. Some part has many features. Yeah. So every time you have a feature, there is a size. Dimension is always there because we are living in a three-dimensional world. Yeah. In the space and time. So therefore, we always have a dimension. All the things that we try to make has the dimensions. Yeah. So therefore, you have to deal with the size. So that's what we call an individual feature or size. Yeah. And let's take a look at that envelope rule. So coordinate dimensions, meaning like dimension. When we talk about coordinate, you're thinking about three-dimensional, yeah, three-dimensional systems, and your dimensions are in there, yeah. So that's how we call it, coordinate dimensions. And of course, every time you have a dimension, I always say this again and again to you, so you should get it by now. You have a ranges, your tolerance, yeah. In these ranges, your dimension is going to stay. Yeah, it can vary in that range. So that's what we're talking about. So we have your upper and lower size limits. We have boundaries because you have a tolerance. So you have upper, lower to make the range of that tolerance. You have boundaries, the same thing as your limits. And in these boundaries, all of the elements of that feature, yeah, got to be in that tolerance range. That's it. Yeah. So that's your rule. Enveloping meaning all the things got to be in that envelope. Yeah. Don't come out of it. So pretty easy and simple. Yeah. So circumstances 1, 2, 3. We have 3 circumstances in this rule. So number 1, size limits. So size limits is very important because it's going to control the extent, yeah, to which that variation in your form is permitted. It's just telling you that you have a limit and don't go beyond that. Okay, keep it in that limit. Form variations, you can't also exceed that limit. Okay, because that limit is completely established or formed by the size dimensions. Yeah, so dimensions, the size form your variations. Variations cannot go over the limits of that tolerance range. Yeah, your form, geometric form, is permitted in that limit, size limit. Okay, so that's what we're reiterating again and again, very similarly. So if you produce, so if you do it at the MMC, so MMC has two, okay, internal features and external feature. So with internal, take the most material, yeah, with external, you're going to take the most material again, but the size limit is going to change according to what. Okay, so even though you're taking the most material in internal feature and external feature, for internal you're going to choose the smaller size, for the external you're going to choose the larger size. Yeah, so right now when you listen to me, you might already forgot what they are, but just stick to the whole area shaped example to visualize it. Okay, start with a very simple example, and then that features you got to have that features in a perfect form. Yeah, meaning like they got to be in that range. Again, they got to be in the range of the tolerance uh, limits. Yeah. Okay, so example root, envelope root. So let's take a look at it with the diagram of course, so you can easily visualize it. So here's the shape and size. We have an object. The object has this view. Okay, we're only two dimension anyway. So you have your width and then your height right here. Yeah. So this is you can also say length. Yeah, doesn't matter what that is. Just a length right here and a height right there. Of course, you know the dimension here, yeah, because this is your dimension line right there, your extension line right here, yeah, your arrowheads right there. So you definitely know, hey, I'm dealing with a dimension, yeah. Sorry, I gotta go and put this. You're dealing with a dimension, and here we go. 0.5 is your range because see this little plus and minus right there. So it's just telling you, hey, you can go down 24 minus 0.5, your lower limit, and then 24 plus 0.5, your upper limit. Okay, so that's your tolerance. And you have two different, see, axis. So this is your y, and then this is your x-axis in your coordinate system. So therefore, you're dealing with this object bilaterally. Yeah. So you have variation in this direction and also in that direction. Okay. So this is your design size of a shape and size of that object within these tolerances. You have two sets of it for the height and also the length. Alright, so now here you have calculated it. Okay, so this one 10.5, the bigger one, 24.5, the bigger upper area limit. So here you can see the boundary of the upper limit, okay, of this tolerance range. So when we draw the upper limit with this little this little dash line right there, you understand that your part cannot go beyond that. Yeah, your part got to be in that, okay, upper limits in two directions, of course, your height and your length. Now we get into smaller, see, smaller range, which is your lower, yeah, which is your lower limits 9.5 and 23.5. Again, of course, your part cannot go smaller than that. So see, your part is between that zone. See, from here all the way to here. This is your maximum, this is your minimum. Lower, this is upper limit. And we call that the range. Yeah? Since we're dealing bilaterally, meaning like your length and height, see this clear zone right there, like a little area right here? Yeah, so your part, yeah, it got to be in that zone, okay? And so we call that tolerance range. Yeah, so the range of acceptable limit. Tolerance meaning like, hey, I can tolerate, your mistake as long as you go between that range. Yeah, your mistake can be lower than the lower limit and bigger than the upper limit, but you can vary in between them. Yeah, I allow you that. So that's what is a range of acceptable limits of science. Yeah, in drawing and of course in manufacturing and machining as well. Okay, so here we go. The actual size of the part can vary within the boundaries. Yeah, we just zone it out. Yep, you see that? Yeah, very clearly. This dash, and here is your part. Yeah, now the part is very close to the lower limit of it. Yeah, but it's still within the limit set by the tolerance acceptable values right in there. Okay. Now the actual size shown here, see now look at that, it's very close to the upper limit, yeah, approaching the upper limit, but it's still within that zone, within that range. So therefore it's okay, yeah. So if the actual size is at your most, most material condition, which is your maximum material condition, MMC, then your form got to be perfect, okay? So so if we put it, of course, closer to the lower limit, then you're going to get the most material, yeah? If that was an internal, right, feature. If you're dealing with external feature, of course, you got to keep it all the way closer to the upper limit of it, yeah? So that will satisfy your MMCs. All right. Okay, another one is the shape. Yeah, the shape is kind of not perfect. A rectangular shape is a little bit different, but again, it is still within that range. See that? Yeah. So geometric form, it can be effective, but it is inside of that range. Okay. Another form, and this is what we call variation of the form. Yeah, but accepted because it is still within that range. Yeah, even if you do this perfect, you do this or this, you're still okay. Yeah, because it's inside that zone. Still, see, this merely defines the envelope size limit. We don't control the form. See, shape is very different. And don't worry too much about it. Just showing you different, different form variations here for you. Okay, 1 and then 2 here. So rule 1, right? Rule 1 is very important because you have to envelope the size limits. Yeah, it doesn't really control the form of that feature, of course. Yeah, within the envelope, which is this range right here, as long as they're in it. But when it comes to dealing with MC, then of course you have to pay attention to have a perfect form, yeah, because that's required in each of the case when you have to deal with the MMC, meaning that you have to be so careful that your part got to be within that range. However, depends on the interior and exterior part of MMC, you're going to control your part either approach to the lower limits or the upper limit, okay? Because you have the external and internal feature of MMC, two conditions going on, even if you're dealing with the maximum material condition. And the other one is your LMC. So the LMC is a full tolerance is available. Okay, then we'll get into the diameter. Yeah, we finished with the very first shape, which is kind of a rectangular in some different forms. So diameter symbol is like this, and here is your dimension. Yeah, range is 3.22 all the way to 3.24. So this is your range, okay? And we also call that your tolerance lower limit, and this is your upper limit, okay? And now we start to draw with the dashed line so you can be able to see the lower limit right there, yeah? So the desired dimension, again, is identified with this lower limit, which is in this case 3.22, yeah? Upper limit, 0.5 not 0, but I mean 3.24, yeah. We can approach to the lower limit, yeah, but it is acceptable as long as it is in the range. We're going to approach to the upper limit, okay? See that? If you're dealing with the external part, yeah, external part feature, like a shed, of course, it's going to be perfect at the upper limit to get your MMC, which is your maximum material condition, okay? Yeah, sorry, the slides is messed up with some, I don't have time to fix it, but you can read it, okay? All right, now here you can see form variation, yeah, starting to show you your actual feature, because your machining could be a little bit different, but it's okay. Still in your tolerance zone, your lower and your upper, 3.22 to 3.24. So here, see, look at this. Another form different, but it's still, you know, in the upper limit and the lower limit, so it's still in these boundaries, okay? So therefore it is acceptable. So rule 1, doesn't really matter what your form is, as long as they stay inside of the range, it's okay, okay? So that's what it's saying. Oh, when a geometric tolerance is applied to the size dimension of a feature, your rule 1 is going to override that, yeah? If you don't have a geometric tolerance, then the actual size, yeah, envelope is going to establish by dimension limits. So this is just telling you, like, if you don't have your geometric tolerance, right, applied to it, then you're just going to go with your actual size. And that applies to all features, yeah, all your size on your part. For rule 1, it's going to apply to individual feature, yeah, individual size feature. But they don't care about the interrelationship between the features. So your rule 1, make sure that you don't go into the relationship or interactions. Yeah, just go with each individual feature on your part with their own dimension and tolerance, of course. All right, let's take a look at this. Here you can be able to see it, just a drawing here. We have a 2-dimension here, and you don't have any kind of control. Yeah. So here, when you look at it, you can't really determine, oh, what is the dimension, what is the tolerance? I have no idea, yeah? But it seems to be like a right, dealing with the a right, in this case, a right angle. So you gotta know where is the tolerance that defined for this part, yeah, or feature. So you're gonna take a look at your title block, yeah, in your drawing. So down there in your title block, you're gonna see the tolerance for angles, talking about, yeah, where the angle can vary, yes, as long as it's around that 90-degree plus or minus something, yeah. So here it's just telling you, hey, if there isn't, yeah, anything identified for the tolerance, go ahead and take a look at that title block, yeah. So rule 1 is going to depends on that title block tolerance, yeah. So the right angle got to be off, or as much as whatever your title block tolerance identifies, yeah, all that limitations right here. So you go with the upper and lower limit of that title block tolerance, defining the title block down there, yeah. So rule 1, again, it doesn't really control your interrelationship. You're just looking at individual feature, yeah. At least you're gonna get that. Rule 1 is gonna control only the limits of size for size dimension for individual feature, yeah. All right, this is just a review, yeah. Interrelationship, that's the orientation between the individual size features. They can only be affected, you know, within the limits imposed by the boundaries set by rule number 1. But we don't really care for it, because rule number 1 is going to override the geometric tolerance, yeah, and associate with the dimension on features of your size, okay. So rule number 1, again, size form controls, yeah, going to apply to all the features of size. Limitations of Rule 1 can be overridden by geometric tolerances. Okay, and you wouldn't get it when you read this. Okay, don't worry about it. Just stick to the tolerance. In practical, all we do is we pay attention to the tolerance range, and of course your MMC and LMC. Just follow by the rules and don't worry too much about this. It will come to you automatically. Okay. Right now, just concentrate on tolerance zone, tolerance limits, always attached to your dimensions. If you cannot find the tolerance limit with the dimension in your diagram, it's got to be over there in the title block. Follow them. Upper limit, lower limit, very important. Everything that you do got to be within that limit, regardless of the perfect feature or variations in form. Okay, because they are acceptable. Yeah, as long as they are in that range of your tolerance. Okay, that's all you need to know for the first part. Yeah. Exception. Okay, exceptions is number one is a free state variation. As you know, yeah, even though we try to keep the part size within the tolerance zone, you have a condition, something called free state variation. So that time the features of size, okay, that size don't maintain their shape. Okay, shape is gonna be different. Yeah. Since they don't maintain their shape, they're not controlled by the rule 1. Yeah. And rule 1 control the individual feature, but it doesn't control the stock size, like your bar stock or rod sizes or size with tubing. Yeah. And a sheet metal thickness or structural shapes at all. Yeah. All right, then we'll get into second rule. Yeah. Second rule is also called the fundamental rule. Yeah, it implied your RFS condition. Your RFS is again regardless of feature size. Yeah. So if you don't have MMC or LMC, yeah, with your tolerance or datum reference, we're just gonna go ahead and use your RFS. Yeah. We're gonna follow the standard is ANSI Y 14.5 M. Yeah. The current standard is ASME Y 14.5 M 1994. Yeah. Your ISO again, don't worry about that too. This will be given to you all the time. Yeah, when you work. So rule 2 number 2A is your alternative practice. So for tolerance of position, your RFS is going to be redundant. This is just comparing with the old standard and new standard. Yeah, so don't worry too much about that. So you have to specify it on your drawing. Yeah, respect to your individual tolerance, datum reference, sometimes both of them. And this is not very important for our course. Yeah, this is just more of a when you start working, just pay attention to what standard we're following, either new or old. Yeah, some of the company, because they're still using referencing the old ANSI Y 14.M. Yeah, 14.5 M 1982 version of it. But don't worry about it right now. We'll just get into the rule. Yeah, straight in. So rule 2 and 2A, yeah, alternative, and rule 2A is your rule 2 alternative. Rule 2 is rule 2. They're used to express the geometric tolerance, okay, in feature control frame. Meaning like we'll be using a control frame is nothing but it's like a little box like this. I show you one by one. So rule 2A again, go with your current standard. And it depends on your company. All right. This is just telling you about your fundamental rules, symbols we use, in geometry dimensioning and tolerance. We call it GD anti, your little pocketbook that I told you to buy right in your syllabus. You need it if you're going to keep your career in this line, because you have to go back to it. You can't remember all of it. We don't remember. No one remembers all of it. We always go back and get in there, and as you draw, you get it, okay? So if you forget something, go back to that little pocket book. Everything is right in there, So geometry characteristic symbols, we're going to hit the feature control frame, modifier control symbols, datum feature, datum target symbols, and also I'll give you the supplementary symbols. All right, let's get into symbols. This is on your third handout. I'm combining the lecture all of it because it's short. Yes. Okay, symbols. This is just kind of like a content for you. So in this order we will cover. So first we'll get into the geometric characteristic symbols. So there are 14 of them, and we are going to take a look at it. So they're divided into 5 categories, 14 geometric characteristic symbols. The first category, form, we're going to deal with these symbols, profile, orientation, location, okay, and then your round out, okay. So all these symbols are put into 1, 2, 3, 4, 5 categories. Altogether, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 geometric, right, characteristic symbols. So this is your geometric characteristic symbol, belongs to the form category, So this one belongs to the profile category. This one belongs to the orientation. And we're going to get into each one of them, So in form, type of control, form, profile, orientation, location, runout, So these are our category, okay? And here is your description. So form, individual feature, profile, individual and related. So relationship is there. Orientation, location, and runout, you have a related features, meaning with the relationship with other stuff, Okay, so geometric characteristic, again, form, we have 1, 2, 3, 4. Here are your symbols. The very first one is just straightness, flatness, circularity, and cylindricity, okay? Then we have profile line, and then you have profile surface. Then in orientation, we have angularity, your angles, perpendicularity, whether they are perpendicular to each other, because they're related features to looking to features you're looking at, parallel, they're parallel to each other. Your position, concentricity, your symmetry, okay? And then we come into our runouts. So we have circular runouts and total runouts, all right? So these are all the symbols that we will be covering, All right, then we will go into the next one. So let's stop here for a while. Okay, so we'll get into feature or control frame. All right, feature control frame. So here is your example. It looks like this, okay? So this is called control frame, so they're placed on a drawing. And because we got to do like this, so you can be able to see the design information and controls in there, organized. So very first one, we're going to put the geometric characteristic symbol right here in our first box, in former term, they use the first cell. We just call it a box, the very first box, which is this guy right here, So first cell, because it is in the form of a table, a little table. So this is your column, of course there's only one column, 2, 3, 4, 5, and then there's a single row right there, So the very first cell, because you have column and rows, we call it the cell when they cross, So the very first cell, I call it just a box. So the first box is your geometric characteristic symbol. That's what we're going to put it in, So this is going to, geometric characteristic symbol is going to show you the control, that is required. Second one is a zone descriptor, The third one is your tolerance value, the fourth one is either we go MMC or LMC or RF, okay, RFS. So here in this case is MMC, which is material condition, yeah, identifier, which is a big M, of course. We don't know that is L or M or S, yeah. It's just showing you the general, oh yeah, we are dealing with a material condition modifier. Primary datum, secondary datum, yeah, another material condition modifier come with it, either MMC, LMC, or RFS, okay? And then here is your tertiary datum. So these are the contents that gotta go into, yeah, your control frame in that order, yeah? Right now, just try to get the order. Okay, so here, sometimes you're gonna see the frame is short like this. So you have your geometric characteristic symbol, and then you have your tolerance value, okay? And we will be giving the datum. See here, I have A, B, and C datums are right in there. And here, we don't have it, okay? So you don't have a datum reference control right there. And we call this type independent controls, yeah? Because you're not measuring from a datum. So this one, in this example, we have a feature, yeah? And we're dealing with the straightness. And that tolerance zone is 0.005 inches, yeah, in unit, British unit. Okay, then the next one is when you deal with your material condition, yeah. This example is showing you your axis control, and that axis got to be within the tolerance zone 0.005 because it's telling you your tolerance value right here, yeah. So teaching you how to read the control frame. When that feature is being controlled, and we have your maximum material condition, but this example is not very good because you don't have any kind of condition given to you. You only have a material condition modifier. So it could be MMC or LMC or RFS, right? But in this example, of course, the author write it like a maximum material condition. So these little things, okay, nobody is perfect. You'll see those kind of little things like that, okay? So anyway, just pay attention that we're only at the M, yeah, M and yes. So that's your material condition at maximum material condition, okay? So if you had like L or something, yeah, you're gonna have your least material condition. If you have S here, you're gonna be dealing with the RFS, okay? So it can be anything for material condition modifier. Of course, in the example, we're just showing you with the maximum material condition. All right, this one, you have two datum, your A and then your B, primary datum, and the secondary datum is B, yeah? So this control, again, is relation, yeah, there's a relation to the primary datum feature and also the secondary datum feature. Your tolerance, again, is 0.005, so that's a linear distance they're apart to each other. Yeah, because here you're dealing with the perpendicularity, because see this sign, yeah? So perpendicular, try to get these signs in your brain for now. If you don't get it, just use a sheet, okay? Just use a sheet, write that down, and eventually you will get it, yeah? All right, next one, we're dealing with this control frame, and here we have our tolerance value, yeah? So we have your material condition modifier, in this example, going with the max, yeah? And your primary datum, secondary, and tertiary ABC right there. And we have no material condition modifier in any, in any of the data. No MMC or LMC or RFS in A, B, or C. So therefore, we are going to maintain that regardless of your datum feature size, yeah? So if you don't have M, if you don't have L here, you just go with your regardless of the datum feature size. Alright, next one, see, oh my god, there's a material condition modifier at datum, yeah? B, which is your secondary datum. So for, this is what I try to tell you, yeah? Even if like we use the S, yeah, and then the circle for the RFS, when you use a control frame, we don't put that in. Yes. So here B, you're gonna have a max. A, go with your regardless of feature size, and C, you're gonna go with the regardless of feature size. Okay. Your tolerance value is 0.005. Okay. Primary datum, go RFS, even if we don't show you S with a circle. Yeah. Secondary, go with the max, and tertiary, go with the RFS. Pretty easy to read. Yeah. Okay. Now the control frame. So we have this, and that. Yeah. So these are all the example. Various ways that we can give the information, yeah, of your feature. Some of the example, you have datum references. Some of the example don't have datum references here. In datum reference, some of them don't have material condition modifier, and some of them have the material condition modifier. Yeah. If you don't have it, just go with RFS. Yeah. If you have it, go with what you have, which is your M, yeah, maximum material condition here. You only have ML, yeah, and S. Sometimes depends on your company, they use the S for RFS. Yeah, I told you several times already. Sometimes they don't, you just go without it. So that depends on the standard they're following. Of course, when we put them in the feature control frames, you're communicating between the engineers and designers and the machinists right there. And we all read the same thing, yeah. So you got to be careful when you write it, yeah. If you were the person to write the control frame. This one is a composite. See how different it is from our regular example here. Why? Because you have another row right there. Yeah, there's a first column. And you have two rows. Yeah. The second column is like a one half, and the other one, yeah, full. Giving you two different information, and that's we call it the composite feature control frame. Yeah. So you have tolerance over the full extent of a part. So we have two different tolerance is going on right there. Yeah. So you have, so this example use only one geometric, yeah, characteristic symbol for two line. Okay, tolerance control, and we call that the composite feature control frame. Right now, just try to get the frame. Yeah, different types of frame. Don't worry about inside yet. Yeah, just worry about what you have to put in the control frame, how we put the control frame information. Okay, and types of control frame. This one is a regular one, and this one is a composite. Okay. Composite, yeah, going into there. Overall, here is your geometry symbol right there. This is your overall surface flatness, because this is your flatness symbol, yeah. It's a don't exceed over 0.4 tolerance, yeah, in this case millimeter going in this example. Flatness again, don't exceed 0.05 in any area, okay, and that's going to measure a 25 millimeter by 25 millimeter. So this is given to you area, and don't exceed this, yeah, tolerance. So that control is going to apply across the entire surface, okay. So that's how you read it, and then we'll see like how we apply that, yeah. So since the name is in there, so where are we going to apply these control frames that we write with all the tolerance and dimensions, right? And geometric symbol. So you're gonna of course apply to the feature, yeah, because it said it, so the control frames are for your feature. So we're gonna apply to the features or features of your size. Your features always has a size, all right, it stays in a particular dimension. That's why you have a tolerance, yeah. So try to use your common sense instead of going into the bulky text, yeah, interpretation and description right here, yeah. So a lot of the students, especially international students, you know, I feel you, because you gotta read it, and then sometimes it won't come into your head, okay, and then you go into confusion and the text right there. Don't worry too much about it. We're learning how to write, yes, drawing specification tolerances, and we use a box, right? We use a box controlled, we call it control frame. It's just a little table giving you everything that you need to know about that feature and the size of the feature and tolerance, okay? And there's a way that you put it in each cell. What information are you going to put? And they come in the order, yeah? So you go with the geometric character, you go with the tolerance, followed by the datum. And each one of them has a material condition modifier, yeah, either MMC, LMC, and if there isn't LMC or MMC, you're gonna just go RFS without the symbol. So things like that, okay. And of course, these control frame we're gonna apply to the features, of course, yeah, on your part. So that's all you need to know. Yes. So since you're applying that to feature, is very much location, yeah, specific. So it's the location and also the application of that feature control frame, yeah, relative to your feature. Feature has a size, so feature of size, and both of them are going to determine how the control is going to be interpreted, applied, or verified. Yeah. So verification is in my line quality control, quality assurance, and systems. So we usually verify if anybody who is doing a machining or engineer or whoever, yeah, so operator, whoever doing, yeah, a particular assignment, are they following the specification? You can check, yeah, with this, okay. So yeah, let's go back in here. So here is your GDT. This is just a little exercise, yeah. You have to identify, okay, which one is related and which one is not related. So you go back to our summary table that I gave it to you, yeah. So each one of them, of course, right now already done it for you, yes. So therefore, straightness is individual, profile is individual, and related circularity is individual. So go all the way to your circular runout, yeah. So let me go back and I'll show you, yeah. So which is this one, okay. Here is your individual or related, yeah. So this table, your 5 categories of your, and that's what we are doing the exercise for, and you have to get it, okay. So perpendicularity, you know that's related because you need to have two in order to measure the perpendicularity. Flatness, the same thing, yeah. So individual, because you don't need another one in order for you to get the flatness. So therefore, that's the individual, yeah. So so these are your symbols, your geometric characteristic symbol, yeah. And you need to know whether they are individual or related control, yeah. Okay. So in your book, you go to the problem 46 and you're going to see the same thing here, yeah? And of course, here I'll just show you how to do it. So when you study, you can be able to get this. It wants you to sketch a feature control frame, yes? So your feature control frame is a little box, yeah? And then go in order according to what your question is going to give you. So you're going to insert the following symbol information. You're going to have to draw the correct geometric symbol, yeah, for position is given to you. And you have your datum B, C, D, okay, and your datum B as a size feature. You have a modifier because it's set so in maximum material condition. Your datum C and D apply the regardless of feature. So with little s in a circle or not, you can write it, yeah, without it. Tolerance zone given to you 0.010, okay, blah blah blah, and you read it. So now you get a whole of what to put into here, yeah. Don't imitate me for now. I'm just too fast because I do it all the time, yeah. For you, of course, you're gonna read each one of them what to put, yeah, because you're still like trying to get the control frame, yeah, in your head. All right, because I don't want to take up your time so much. So when we're lecturing, we have to use this time, yeah, carefully, so you don't get so bogged down. So the maximum lecture time is about one and a half hours. Yeah, I try to keep it down under that. So here. So in your given example, we're going to put in each one of them is a position, the position symbol. Tolerance is given to you, which is right here, 0.010. It comes with the material condition MMC, so put that in there for you, yeah? And that you're dealing with a cylinder, so therefore you got to put your cylinder symbol right in here. You have your datum C and B, and then your D. Your B, okay, secondary datum, all right, has a material condition, which is a max, see? Set it so here, B with the max. So therefore, I just read like B with the max. I don't even read any of that, yeah, to make it faster. So B. And then your C doesn't have, so regardless of feature, bang, bang. I'm following the standard and I don't need to put S suckle in there with it, yeah. Some student want to put it, that's okay too. All right, the next one is another problem of 47 in your textbook, yeah. And of course, this is just choosing, true and false here in this case, of course. And yes, this one I want you to do it by yourself. Okay, so here is the answer. The answer is given to you in the PDF, so you can go ahead and read, listen to the lecture, read the PDF, and be able to PDF me my handout. Yeah, so and after that you can be able to do this exercise. Yeah, so I'm not gonna go each one of them for you here. All right, then we'll go into the placement. Yeah, feature control your frame placement. So how are we going to place it? So example number 1 is given to you here with your control frame. Your control frame is, look at this, only 2 without the datum, yeah? So that's applied to the surface, okay? It set it so here with this little, leader head right there, note. And we're going to apply the rule number 1 right in here, yeah? So this control, example 1, want to know where does it apply to? It applies to here, right there, because it's set it so with this arrow. It said this control frame is for that surface, okay? Here, look at that. This is a completely different way, see, of showing example 1 and 2. In example 2, look at this control frame. Look at the arrow go down. It has no surface on it. It's just showing you, look at this. This is your extension, yeah? So therefore, you're dealing with the dimension. So therefore, the feature size, yeah? So like I said, when you read a feature of size, you won't get it. So when you actually look at the diagram, you got it, yeah? Everything come to you. So telling you here, right there, this one only on the surface. This control frame applies to you. Don't worry about what's in it yet. This control frame is for your surface. This control frame is for a feature size because it said it so. Where is the size? I don't know. Where does it say? It said it so right here because this is your dimension line. This is your extension line. Dimension and extension lines always tell you the dimension value, which is right here. Yeah. So therefore, you know that you're dealing with a size. Yeah. So that's where we talk about the limit of size, upper limit, upper size, and then the lower limit, your lower size. We're talking about the feature size, okay? So now you got it. So again, your zone is telling you the actual size got to be within that limit, okay? Within that zone, within that tolerance, because you are tolerating in between there, yeah? You will not tolerate if it goes up or down, yeah? Outside of that zone. All right, this is just your concept to remember. This is just reiterating what we have just gone over, yeah, so you can read it in your handout. Yeah, I'm not going to go over it again, yeah. It's just reiterating the rule number 1, your envelope rule. All right, now we'll get into the modifier control symbols a little bit. See, right here now. That's just a table of content. All right, modifier symbol looks like this. Yeah, see, this is our symbol. Maximum, we already knew this symbol. Least, yeah, which is your least material condition. And your P is your projected. These are new ones. So projected tolerance zone. Free state is your F. Tangent, all right. Plane is your tangent plane. Usually you can see it, yeah, your circumference of your circle. And then, of course, this is another circle, yeah, diameter of the circle, and you know this. You have radius, yeah, diameter, yeah, spherical radius, spherical diameter, little s on it, yeah. But don't forget all of your symbol. Then, of course, we will get into the datum feature and datum target symbols. So I'm going to stop the first part of the lecture right here. Yeah, I don't want to go over 1.5 hours too long, so I usually cut it around 1, yes. So we have covered all the way to handout 5, yeah? All right.